In the previous episode, we finished building up the clock selector and multiplexer on the breadboard. This now allows me to put the clock generator into a single stepping mode where we can trigger individual clock cycles manually, and the free running mode where the clock just runs at a tunable frequency. Those clock modes will be vital for debugging the Superscalar out-of-order processor as we start to design and build it. Be sure to like and subscribe if you want to see how this project unfolds. But we're not entirely done with this breadboard yet. With our nice clock generator all set up and working, there's one last topic we need to look at, and that's resetting our CPU. Many of the storage chips like flip-flops and counters, which we'll use throughout the CPU build, have a dedicated signal to reset them to a known state. This counter chip down here, which we've used to test our clock generator, had a reset input. Whenever this input is high, the counter goes back to 0. This happens regardless of what the clock is doing. As soon as the reset goes high, the count goes to 0, even if there's no clock happening. And the count stays 0, even if the clock is happening, as long as the reset is held. In digital circuit design, this is called an active high asynchronous reset. Generally, a reset is active high if pulling it high causes the chip to reset, or active low if pulling it low does the trick. Besides that, a reset is asynchronous if it immediately resets the chip as soon as it is triggered, without the need for a clock edge to occur. And it's synchronous if the chip resets on a clock edge while the reset line is active. Now for our CPU, we want to have a reset button that we can push to put the CPU back into an initial state and have it restart execution. We could just hook up a button to the reset inputs of the chips in our design and call it a day. The problem with that though is signal timing. Me pushing this button down is going to cause the reset to immediately activate, which is good. But when I release the button, it will also immediately deactivate, which is bad. That's because the clock will keep toggling, and that release of the reset will happen randomly somewhere within the clock cycle. If that's far away from the clock edge, all is well. But if the reset releases right about the same time the clock goes high, some of the flip-flops might already say, nice, I'm out of reset, let me update my state. While some others might stay in reset for another cycle. This happens because not all flip-flops receive the reset and clock signals at the exact same time, but there's a slight variation in the delay as the signals make their way across the breadboards and wires. This is a big problem because it desynchronizes the circuit in a sense. Some of the flip-flops will already have advanced to the next state, while other flip-flops are still in reset. This breaks the fundamental assumption of synchronous hardware design. What we need is a bit of hardware that synchronizes the reset to the clock, such that it releases at a safe time during a clock cycle. These reset synchronizers are used very often in digital circuits, and our CPU isn't going to be any different. One of the simplest ways to build a reset synchronizer is with a bunch of flip-flops. We have our button hooked up to the reset of all the flip-flops, hardwire the first flip-flop's input to 1, and then arrange the remaining flip-flops in a chain. What will happen when we push the reset button is that all flip-flops reset to 0. Then, as the clock ticks, that 1 we have connected to the first flip-flop will start to shift through the chain and eventually make it to the last flip-flop. That last flip-flop's output will be our synchronized reset. By picking the number of flip-flops in the chain, we can decide for how many clock cycles the reset will remain low until it releases. So let's build this up on the breadboard. First, we want a reset button. Connect that to ground on one side, because the reset of our flip-flops is going to be active low. And add a pull-up resistor to VDD on the other side. I'm going to use the 74HC175 chip, which contains 4 flip-flops with a common reset and clock pin, and inverted and non-inverted outputs for each flip-flop. That will give us quick access to an active high and an active low reset signal in our design. So let's put this down and connect up power and ground. Then we'll want to feed that reset on pin 1 directly from the button. The data input of the first flip-flop on pin 4 will want to connect to VDD, and then hook up the flip-flops into a chain by connecting the output of 1 to the input of the next. That's the first output on pin 2 going to the second input on pin 5, the second output on pin 7 going to the third input on pin 12, and the third output on pin 10 going to the fourth input on pin 13. The outputs of the last flip-flop are our synchronized reset signals. Pin 15 is active low and pin 14 is active high. Let's hook up an LED so we can observe the reset state along with the generated clock. Let's hook up our active high reset output to the counter circuit down here. And we'll also want to connect the clock input of the flip-flops on pin 9 to the output of the clock multiplexer. Alright, let's power this up and see if it works. First, I'll switch to single stepping mode so we can control the clock. Then hit the reset button, which causes the reset line to go high. That causes the counter to go into reset state. Now, it should take 4 clock ticks until the reset drops to 0. 1, 2, 3, 4, and the reset goes off, and the counter starts counting. Awesome! We can also switch over to the free running clock. And when we hit the reset button, the reset line activates. 4 ticks pass, and it deactivates again. Very nice. These clocking options and the properly synchronized reset are going to be a big help building the CPU. Now that things work, let me clean up those wires a bit again. One thing that's bugging me is that the entire breadboard starts up in some arbitrary state when we power it up. Sometimes it's in stepping mode, sometimes it's in free running mode, and the reset shift register contains an arbitrary mixture of ones and zeros. I'd like this thing to power up into a reasonable state, say single stepping mode with the reset line activated. So what we need is something that does the same thing as pushing that step mode button and reset button on power up. We can achieve this effect by connecting a small capacitor between the button and ground. The capacitors to ground act like a short circuit because they are fully discharged, effectively tapping the button for us. But then they will quickly charge through the pull-up resistors. And when the circuit is powered down again, the capacitor will slowly discharge itself, through parasitic effects, but also through the rest of the circuit. I'm going to place a 10 nanofarad capacitor here across the step mode button and over here across the reset button. And now when we power the breadboard up a couple of times, it will reliably switch to step mode with the reset line activated. Great, this works like a charm. At this point, the clock generator breadboard here is pretty much complete and ready for use in the CPU. It has a bunch of pretty useful features. On the far left, there's the step button, which generates a single clock pulse, which will be handy for debugging circuits. To make this work, we had to use a 555 timer chip and a filter capacitor to get rid of the unwanted bounce in the button's metal contacts. There's also a free running clock, implemented again with a 555 timer chip, where we can use this variable resistor to dial in the clock speed we want the CPU to run at. Next to these clock sources, we have the selector buttons, which allow me to either put the clock generator into step mode, where the clock essentially halts and waits to be triggered through the step button, and the run mode, where the tunable clock takes over. We've used 2 NAND gates to implement the clock selector, which is essentially just an SR latch that keeps track of which mode is active. Then we've used 3 NAND gates to build a clock multiplexer, which feeds either the single stepping or the free running clock through to an output pin, based on the output of the clock selector. And as a final consideration, we've looked into generating a clean reset signal in this episode, and added this reset synchronizer over here, which is basically just a chain of flip-flops that keep the CPU's reset line active for a fixed number of clock cycles, and, importantly, releases the reset at a proper point in time. As a result, the breadboard produces a clock output, indicated by the blue LED here, and the reset output, indicated by the red LED. With this clock generator all set up and running, we can now start to design and build the actual CPU. In the next video, I'd like to look at a few of the core principles of executing a program, and come up with a program counter that we can use to run through a list of instructions. Thanks a lot for watching, like and subscribe if you'd like to see more of this, and see you next time.